All right, we are going to do a little brief introduction to an important application of integration um, called differential equations. Many of you will take an entire course, if not many courses, on differential equations. This is an area that is rich in application, especially in engineering and the sciences, computer science, mathematics, lots of different areas. And so, what is a differential equation? First of all, it's just an equation where the unknown quantities we're looking for, they're not a variable, but they're a function. So a lot of times we're solving equations, we think of the variable, of 3x plus 7 equals 10. What is the value of x? We're looking for a real number. Here we're looking for functions, so the answer here will be a function like sine of x, or the function x squared plus 2, or something like that. So the differential equation contains that unknown function. That's the variable quantity, really, is sometimes called the dependent variable in that case. And it may include and it's going to include one or more of its derivatives. And by derivatives in plural, I mean first derivative, second derivative, and so on. The order of the differential equation is the order of the highest derivative that occurs. So if the first derivative is there, it's called a first order differential equation. Second derivative is the highest order, second order. Here are some examples. You see this differential equation. The function is y that we're looking for, and here's its derivative. So this is a first order derivative. The dependent variable, right, again, is the function y we're looking for. The independent variable, then, y would be a function of what? Since you don't see the independent variable in this equation, we can just use x. It's understood to be x. But here we have a second order differential equation. Notice we have the second derivative there. And again, x could be our independent variable. Here now we're clearly told that x is the independent variable because I've got dy dx, right? So dy dx is the first derivative, so this is a first order differential equation, but this clearly tells us the independent variable is x. Y is the dependent variable, is the function we're looking for. We're looking for y as a function of x. Here we've got d squared x dt, that's the dt squared, that's the second derivative of x with respect to t. Notice t now is our independent variable. This is an important equation. Actually, some of you might already have dealt with this. Basically, if x is the displacement of a mass in a spring system, this is the equation that models its motion. Basically, its position, if you will. K here is a constant that is called the spring constant, and this really represents what the second derivative of the position is, the acceleration. This is mass times acceleration, which is force. And so there's lots of application in physics and other areas, mechanics. We're going to restrict our discussion just to first order differential equations, so we won't deal with these. If you take the course in differential equations, you will certainly deal with second order and higher differential equations. We're going to focus just on first order ones. So when we talk about a solution, right, to a differential equation, basically we're plugging in that function, y is a function of x, for instance, in and its derivatives, right? We just plug in those values and make sure this is a true statement. Okay, so unlike when we're plugging in values into an equation, real numbered values, we're getting two numbers that are hopefully equal, right? Both sides being equal. Here we're hoping I get, for instance, x squared plus 1 over here and x squared plus 1 over here. So we're getting an identity, basically. We've actually been dealing with differential equations, right? Those are the form y prime equals a function of x, because all I need to do is integrate, right? Because if y prime is f of x, then y is the antiderivative of f of x. So this is really a differential equation, a first order differential equation. But we're going to look at some differential equations of the form y prime is a function of both x and y, like you can see up in these cases here, right? The derivative is a function of both x and y. So this is going to just be a tip of the iceberg sort of look at it, but one thing for sure, if you say you have a solution, you should be able to check it, and that's where we begin with. We're going to show that every member of the family of functions y equal 2x plus 2 plus c e to the x is a solution to this differential equation. Okay, c is a constant here, and you're not surprised to see constants here, because when we solve this differential equation, right, by integrating, we're going to get that plus c constant of integration. Okay, so this has a plus c e to the x, and so sometimes that constant is you know, engaged a little bit differently than we'll see that we're used to seeing with just straight up problems we've dealt with integrating. So how do we solve this? Well, I'm going to plug this solution into this equation. Well, I've got y, so I know what y is. I need to find y prime. So let's find y prime. It's the derivative of this with respect to x. So the derivative of 2x is 2. The derivative of 2 is 0. That's a constant. And the derivative of c is a constant times e to the x, constant multiple. C derivative of e to the x is e to the x. All right, so that's just the derivative. So you will, again, this is an application of derivatives, so you need to be able to derivative and integration. So you're going to have to be able to apply those things that we've learned. All right, now we're just going to plug in. And so I've got y prime, which is 2 plus c e to the x, right? So that's y prime, equals y, and what's y? Just recopy. Minus 2x, right? That's what it says. Y prime equals y minus 2x. And now, are both of these equal to one another? Well, I've got 2x minus 2x. Yeah, this thing simplifies down to just what? Just 2 plus c e to the x. And we notice that this is an identity, right? Both sides are exactly equal for all values of x. Okay, and that's important. We're getting functions that have to be the same, and that means both sides have to be equal for all values of x. And that's clear. So we indeed know we have a solution. Now, how do we get that solution? Well, we'll talk a little bit about that here in a minute, but I want you to just know, regardless of the method that you learn and use, you will always be able to check your solution. Here's a slightly different variety of problem. For what values of r does this function satisfy this differential equation? Notice this is a second order differential equation. I said we were going to be focusing just on first order, but I just want to show you how you can apply this idea of checking a solution to any really differential equation. Here I'm going to need both the derivative and the second derivative, and r is a constant. So when I take y prime, the derivative with respect to t, I've got to use chain rule, right? The outer function is e to the u. So the derivative of the outer function is e to the u, where u is rt, times what? Times the derivative with respect to t of rt. Okay. Notice our independent variable here is t. And of course the derivative with respect to t of rt is r. And so I get r e to the rt for that. What about y double prime? Let's do that over here. So second derivative. When I take the derivative of this, r is a constant multiple, so I pull it out. And then what's the derivative of e to the rt? Well, I just did that. That's r e to the rt times r. So r times r squared e to the rt. You can sort of see how that would continue if we were to continue to take those derivatives. Well, now we plug in, right? So I've got y double prime, which is r squared e to the rt, minus 3 y prime, which is r e to the rt, plus 2y, and y was the original function, e to the rt. Okay. So now I'm trying to find out what values of r make this equation true for all values of t. Well, notice I can do some factoring. I've got it set equal to 0, so that's good. I've got an e to the rt that is common to all of these. I factor that thing out. And then I can further factor this quadratic second degree polynomial right here. Right? I can go ahead and factor that, it turns out, right? That factors pretty easy, doesn't it? Factors is what? R minus 2 times r minus 1, right? Negative times negative to get to positive, right? Negative 2 times negative 1 is positive 2. The sum adds to negative 3. And so now that I have a product of three things equal to 0, then we know one of these things have to be 0. E to the rt is always a positive output, right? The range is all real numbers greater than 0. So r minus 2 is 0 when r is 2, and r minus 1 is 0 when r is 1. So our answer is, these are the values of r. So I've got actually two forms of a solution to this from this. I've got y is what? Equal to e to the t, and y is equal to e to the 2t. Both of those will satisfy this differential equation. Pretty cool stuff. Let's do one more. Show that y equal tangent x is a solution to this first order differential equation. Okay, well, let's find the derivative. We need that. The derivative of tangent is what? Secant squared x. So now, that's pretty simple. Plug that in there for y prime. I get secant squared x equals y squared, and y is tangent x, so that's tangent squared x plus 1. Well, is this true always? I mean, this side doesn't look exactly like this, but if we look at this long enough, this should ring a bell. This should be familiar, especially thinking back to our trigonometric substitution method. And in fact, this basically is a Pythagorean identity, isn't it? This is a Pythagorean identity. It is always true, right, that secant squared x is equal to tangent squared x plus 1. That comes from what? Sine squared x plus cosine squared x is 1. Similarly, we have this relationship between tangent and secant. And so y equal tangent x is a solution. So sometimes we're using trig identities to help verify that indeed we have an identity. Okay, so again, we can plug in and check in various ways, and you should practice that with the problems in the homework. Now, when we talk about the solutions to differential equations, and we get that they are what we call families of functions, right? Because they have this constant that appears, as you've seen in that first example over here, where we had this, plus c here, plus c e to the x here, and we're not surprised again by that. We call such solutions general solutions, but typically we're interested in one particular solution that satisfies some initial condition. This should be y sub 0. Some initial condition. In other words, this x sub 0 or x naught, the initial value of x gives us some initial value of y. So that fixes the actual function we're looking for. And such problems are called initial value problems. So a lot of times in engineering you have a quantity that's changing with respect to time, and we want to understand that function, know what it is. And we also have, at this point in time, right, when we start the clock, so to speak, the initial time, this is the value of that quantity. This is the value of that function. And so as time progresses, then that changes, but we have some starting point. That's why it's called an initial value problem. So I want to go back to the problem we were just looking at, and that is, right, we showed that this was indeed, this right here was a solution to this differential equation. So again, looking at that same differential equation here, with this initial condition, what would we have? Well, I'm going to plug in x is 0, so that's the value of x, and this will be the value of y, our initial values, so to speak, right? And I'm going to plug them into this general solution. So I've got when let's do it this way: 2 times x, which is 0, plus 2 plus c e to the x, which is 0. That's going to be y, which is also 0. Okay, this is saying when x is 0, y is 0. So we get an equation now that we can solve for c, because e to the 0 is not 0. Of course, it's 1. Of course, this is indeed 0, and I'm left with 2 plus c equals 0. And so we know c is negative 2. So the solution, the particular, I guess we should say, solution is, right, writing it out, y is equal to 2x plus 2 plus c, but c is negative 2, so plus a negative, minus 2 e to the t. and that's the particular solution. So the value of c is -2. So that's the particular solution we're looking for. Similarly, we can find the particular solution for this initial condition. What if y of 0 is initially 3? What if when x is 0, y is 3? So now I plug in x is 0 again. Of course, we're going to get the same thing over on this side, but we're going to set it equal to 3. And so this gives me 2 plus c is equal to 3. And so c is equal to 1. And our solution then is y is, replacing c with 1, going to be 2x plus 2 plus e to the, I did t up here, sorry, that should be x. Sorry about that. I don't know where that, actually I changed the variable from what I was using before, excuse me. So that should have been x there. X down here. Okay. So initial value problems. Okay. So now we're ready to go. We've talked about general solutions, particular solutions, how to check solutions. Now we want to look at a method. And the method we're going to talk about is known as separation of variables. It is a method that's used for first order differential equations of this form. Y prime equals f of xy, where f of xy is separable. And separable means what? Means this function can be written as a product of two functions, one that depends on x alone and one depends on y alone. We can separate that into a product. So dy dx now can be written as g of x times f of y. So g is a function of x, f is a function of y. So if we could do that, then we can use this method. Okay, so not all first order differential equations of this form are separable. Okay, so let's just suppose that f of y is not equal to 0, which would, of course, if f of y is equal to 0, this whole thing is 0. dy dx equaling 0 means y must just be what? A constant. Y is a constant function if the derivative is 0. So obviously we can assume f of y is not 0. Then we can define h of y to be the reciprocal of f of y, which I can do since f of y is not 0, and just rewrite it this way, right? F of y is going to be the reciprocal 1 over h of y. And so now what I'm going to do is I'm going to rewrite this in differential form, almost like I'm going to cross multiply in a way, is what this is, what you're thinking about here. But I've got multiplying both sides by h of y dy, multiply both sides by dx, g of x dx. And we use this differential form a lot, like in the substitution method or in integration by parts, and so it's something that we're used to, I hope, at this point. Now what do? We integrate both sides. Okay, as long as we're able to integrate here, then we can get y at least implicitly in terms of x. We may be able to solve explicitly for y in terms of x, and if we can, we should do that. Of course, the question is, what if we encounter a function h of y or g of x that we can't integrate? Well, then this method doesn't help us. So not only does the function have to be separable that we're looking at in this differential equation, but the resulting integrals have to be ones that we can do. Okay, and of course this is where what we've learned so far comes into play. This is applying that integration technique. So let's take a look at an example here. We'll solve this differential equation using the separation of variables. Is this separable? Can I write this over here? Notice I got to get dy dx all by itself, the derivative set equal to this function of x and y. Can I split up this function into a product that is a function of x only and a function of y only? Yes. I can write this as x times 1 divided by y squared, right? This is my g of x, if you will, and this is my f of y from my previous discussion. Function only of x, function of only of y. So it is separable, and now what I want to do is get all the y stuff on one side and all the x stuff on the other. So if I got, let's just rewrite this, dy dx is equal to x over y squared. I'm going to multiply both sides by y squared and multiply both sides by x. Does everyone see that? I hope. And I've got all my y's on this side and all my x's over this side. Now I can integrate both sides. And these are easy integrations, right? What's the antiderivative of y squared? It's 1/3 y cubed, okay? Plus a constant, but what I'm going to do is, since I'm integrating both sides, I'm going to throw the constant here over to this side and combine it with the constant I get here. So I'll still just have a constant here. Antiderivative of x is 1/2 x squared plus my constant, right? So there it is. I have y implicitly given as a function of x, but I can solve for y. I can solve for y to get it explicitly in this case. Multiply both sides by 3, right? And when I multiply by 3, I get 3/2 x squared plus 3c, right? If I distribute that through. Now this 3c, is just another constant. I can just call it maybe c sub 1 or something. It's not equal to c, it's 3 times c, but I'll just call it c sub 1. And then what, to solve for y, I take the cube root. Okay, now there's the solution. This c sub 1 is that floating constant. Now if you look in the back of the book, you might see this, instead of c1 you might see just a c or a k. It doesn't really matter, what you choose for your constant of integration. Sometimes you'll see this, this could be c or k or whatever constant of integration. So we use c almost invariably, right, when we're talking about the constant of integration, but sometimes they'll use other letters as well. It just depends on the situation. So if you see some c or k there and you've got c1 or vice versa, then you're still fine. Okay, but this is it. And furthermore, you could check, you could take the derivative of this function and plug it into back into this equation and replace y with the this function and its derivative dy dx over on this side. Simplify both sides and show that they're equal. Okay, you should be able to do that based on what we did just a little bit ago. Okay, let's take a look at this one here. This one's also clearly separable. It's already a function of x squared, times a function of y. Okay, this time I'm going to multiply both sides by dx, but I have to divide by y to get it over here, right? So I get dy divided by y equals x squared dx, right? Divide by y and multiply by dx. Now I integrate. Well, what's the integral of 1 over y? That's the natural log absolute value of y, right? Plus a constant. Again, I'm going to throw the constant to the other side. Antiderivative of x squared. And there I have implicitly y given as a function of x. But I want to solve for y again. Can I solve for y? Yes, I can. How do I get rid of the natural log? I need to apply the natural base, right? The e to the whatever, right? So I'm going to take both sides, e to the natural log absolute value of y equals e to the 1/3 x cubed plus c, the whole thing. Of course, this is just the absolute value of y. And this I'm going to rewrite, okay? E to this sum is the same as e to the 1/3 x cubed times e to the c, right? Because when you're multiplying like bases to different powers, what do we do with these powers? We add them together, right? So this is the same as this. And I do this because e to the c, that's just another constant. I'm going to call that, again, say c1. It's just a constant. It's just a constant, okay? And so I've got c1 times e to this stuff, and I've got the absolute value of y. I want y by itself. Well, I can do that. I can solve for y. If I get rid of that, that just means that this stuff can be either what? Positive or negative c1 e to the 1/3 x cubed. So in other words, if this is positive or negative, I'm going to get the same thing, right, when I take the absolute value. But again, I'll just note plus or minus c sub 1. Well, either way, plus or minus c sub 1 is just a constant. Let's just call that k. I don't know, right? It's some constant, some constant. I want to call it c again or whatever. Just, since I called c this, I'm just going to call it something else. But the bottom line is then we have our solution. Y is some constant, I'm calling k, e to the 1/3 x cubed. Okay, and you should check. You should check, right, that this indeed works. You know, in fact, let me check this. Let me check that this works real quick. Okay, dy dx. I got y. What's dy dx? Dy dx. Well, it's going to be by the chain rule. I've got a constant multiple k, so it's going to be k times what? E to the u is the outer function, so the derivative of e to the u is e to the u. But then times what? The derivative of the inner function. What's the derivative of 1/3 x cubed? Bring the 3 down. 3 times a third is 1, x squared, right? This is this thing. Okay. And so now if I check, I've got dy dx, which is going to be, let's bring the x squared over here, k x squared e to the 1/3 x cubed. That's the derivative, right? Equals x squared times y. X squared times y. And what was y again? Y was this. Okay. Well, are these two things equal? Yes, right? It checks, right? I mean, I can just distribute this x or multiply by x squared and I get the same thing. Okay. So easy check. Easy check. Okay. Let's do a couple more. Actually, I'm going to stop the video now. We'll do the next video. We'll do the last two problems, so I don't want this to get too long. So we've done a couple here. Let's come back and we'll do a couple more in the next video.